Hi everyone, so today we're going to be going over Vuforia algorithms and implementing them into code. So here I have my Android Studio opened up. But before we get into that, I realize that some of you guys may not be too familiar with FTC programming, like structurally, so I want to just give a brief overview of that. So FTC has provided us with this SDK that has a lot of classes that basically allow us to interact with motors, sensors, without having to worry too much about those implementation details. And all we really have to worry about, well, you do have to implement some methods such as allowing the robot to move forward, backwards, and strafe using by applying certain motor powers. But like really, when you're coding an algorithm to make a robot do a specific action, you just have to think about the certain sub actions, or like try to decompose the problem into certain sub actions and think about how you can do that with sensors or motors. So you don't have to worry too much about the specific or technical implementation details. You just want to think more about the process, I think, and that's generally what you're going to see in FTC code. So hopefully that made some level of sense. And here also, FTC in the SDK, in the SDK, they've provided us with a bunch of samples here. So as you can see, there are a ton with also a bunch of different sample classes for sensors. So you can take a look at those. There are a lot of sensors here. But right now I'm looking at the Concept Euphoria Ultimate Goal Navigation Webcam sample. So basically this is going to be the sample for Vuforia target detection using the webcam, since our robot uses a webcam, but you can also alternatively use this one if you are using a phone. But yeah, so a few things to note, and then after we do those basic things, I'll get into the actual algorithm. Pretty much every program you see in FTC is going to start with this sort of line. So at teleop, which is specifying it's a teleop program, if you had an autonomous, you could just change this to autonomous. And then name equals ultimate goal Vuforia nav webcam. So on the phone, this is actually going to show up as the name on the phone when you're in the menu. So if you wanted to select that, you could just click on that name. Then group equals concept. So on the phone, there's a bunch of different groupings that you can. So if you have a bunch of programs that are similar in function or classification somehow, you could just group them all under some certain name. And then at disable, don't worry about it for now, but basically when we're on the phone, this program won't be shown. And then public class concept Vuforia, so I'm not going to read all of it out, but basically it should correlate somewhat with this, or it should be somewhat similar to the name you gave here. And it extends linear op mode. So in FTC there are two types of op modes, or main op modes, so linear op modes and iterative op modes. So generally, or it used to be at least, so iterative op modes, meaning, so if you're familiar with the word iteration, iterative op modes used to have like loops and loops, and that's usually what are a bunch of loops, I guess. And teleop is like a type of program that sort of loops through the same code over and over, like a listener, constantly checking for certain inputs. So usually teleop would actually be an iterative op mode, but in recent years I think most programs actually come under this linear op mode type. But I'm not going to go too much into the specifics of that, just because it's not very important. And yeah, but there you go. Those are just like the two big things that most will have at the start of their program. And then now I'm actually just going to go on to our algorithm. I guess I'll do localization with Vuforia first. So here you can see I have at autonomous because I programmed this as an autonomous code, and name equals moving to launcher point, and extends gyro2 methods. Basically I coded or gyro methods too, I coded a bunch of methods using the IMU, which is the inbuilt gyroscope in the hub. And so I coded a bunch of methods, and I just wanted this class to be able to access those methods, so I just extended it. And gyro methods 2 is a linear op mode, so just as a heads up. So here, by the way, something I forgot to mention is I used the sample class that we were looking at before and adapted it to my own needs. So that's something you might see sometimes. You use a sample class and then change it depending on how you want to use it or what sort of functionality you need. But yeah, I copied some of the code from that sample, and then so here it says important if you are using a USB webcam, which we are in this case. You must select camera choice equals back, and phone is portrait equals false. So there you go. And then here we're just putting in our Vuforia key, and this is just defining a bunch of constants. I'm not going to go over this too much because it's really not that important for the algorithm. I'm gonna keep scrolling down. If you're, let's see, so yeah, so far so good. So, and okay, one more thing I forgot to mention. So run op mode is really where you have the meat of your code in, so everything inside of here self-explanatory is run. So here we're initializing our robot as specified, resetting the angle, okay, and then a bunch of initialization stuff that I'm not going to get into just because it's not important. So this list, we'll see this later, but basically this list will be storing the target target information into one sort of accessible list. So that's nice. A lot more initialization. Alright. And here, okay, so this is pretty important. So if your camera is displaced, meaning it's in 100% of the time, I'd say it's like not going to be at the robot center. So you want to specify that, and the SDK has provided these really nice variables for you to do that. So it's so you have a forward displacement, vertical displacement, left displacement, and so you would have to change these depending on where your camera is on the robot. So I filled those in, and alright, so that's pretty much all of the initialization stuff. The main thing I think that's important to note because is the camera displacement is important to note, and yeah, I think that's pretty much the big thing here, and pretty much everything else was provided in the sample class, so I wouldn't be too worried about it. Alright, so wait for start. Basically we're waiting for the user to press the start button. So here I've made two variables called target x and target y. So I want my robot to move to the coordinate. Let me just type that. I want my robot to move to the coordinate 10, -50 on this sort of xy plane that is our playing field. So, and then I also created a variable for the power. So power can be anywhere between -1 and 1, with -1 being sort of this backwards movement. So I put it at 0.3. Correction, I'll talk about this a little bit later, but basically when we're using our gyro sensor, we want to specify how much or how fast it's the robot's going to be correcting itself. So that's the variable for that. And then I created two Boolean variables called xFinished and yFinished. So if the robot has reached the x coordinate, xFinished will be true, and if the robot has reached its y coordinate, the yFinished will be true. And while not stop is requested, So until we press the stop button or the autonomous timer runs out. So target visible equals false. Basically, initially you won't have any targets visible, and then for Vuforia trackable in all trackables, so that's what this reads as, or for each trackable in all trackables, if the trackable, which is this image target, by the way, I forgot to specify that, but we're basically saying for each image in all the images that our robot is able to see, for each image in the list of images, if our robot is able to see that image, then say we have this visible target and then get its name, and then target visible is going to be equal to true. Then this line is a little bit complicated, so I'm not going to get into the nuances of it, but basically what this is doing is it's using the information from that image and telling us the location of this robot, and we'll be using that a little bit later. And then this variable called last location stores the robot's current location, and if this line isn't able to actually get the robot's updated location, it'll be equal to null, which is why this if statement is here, to check if it's not equal to null. And then while the target is visible and the op mode is active, meaning we haven't pressed the stop button pretty much, for now don't worry too much about this line, but basically vector f translation is storing our, I'm gonna actually write that, our x, y, and z coordinates, and yeah, and then we use that over here. So we're updating it, saying these are our x, y, z coordinates in inches in this line here, and telemetry.add data is just sending that data to the phone. Yeah, so now we want to move to the x coordinate, so the target x coordinate, which we had up here. So if not x finished, and then let's look at this if statement first. If translation.getZero is the x coordinate of the robot right now, and okay, so and something you might notice is we're always dividing by millimeters per inch. That's just because we want to convert this value into inches because it's in millimeters by default. So now I'm going to explain something a little bit tricky. Basically, what this if statement is doing, so let me just read it. So, and in your mind, replace this translation.get 0 divided by per inch with replace it with current x coordinate. So if the current x coordinate is less than the target x plus 1 and it's greater than the target x minus 1. So basically, if the current x coordinate is within a 1 inch threshold of the target x, then you basically want to say we've made it to this x coordinate. And the reason we have to set this threshold is if we wanted to actually make it so the x coordinate is equal to the target x, well, we might actually end up staying in this loop for a while, because factors like momentum, for example, can make it so we move off of the target x and then we go through this loop again and again. So we want to have this sort of leeway, so of 1 inch, to make sure that the robot will actually, or the program will actually exit this loop or finish the x coordinate. So basically, we're checking if the robot is within 1 inch of the x coordinate, and if it's not, then we're going to check if the robot is x coordinates greater than the target x, and we're going to move backwards. So, and keep in mind we're moving backwards because like of how the playing field is, because like x is sort of that up and down axis and y is that left and right axis. So we're going to want to move backwards to try and reduce our x coordinate. So that's what this is doing, and actually I'll go over this really quick. So here we're setting the powers so the robot moves backwards, and what these two if statements are doing are basically, so robot.getAngle is checking the current angle of the robot from the IMU, and basically it's going to try and self-correct itself if it's leaning too far to the left or too far to the right depending on the angle. So that's what that correction variable we had before is doing. So yeah, so, and this was like, I'd say this sort of process here was determined sort of experimentally for our robot, and yeah, but basically we're correcting the powers so the robot leans slightly towards the left or right depending on the angle to try and straighten it out. So yeah, so, and that's what happens if the robot's above the target x, and if it's below the target x, then we're going to want to sorry, I think I messed up here. So yeah, okay, so move backwards if the robot is above the target x, and move forwards if it's below the target x. So here we're moving forwards if it's below the target's x, or target x. So here, this is the line that makes the robot move forward, and here we're checking if the robot's current position is below the target x. So yeah, sorry if this code is a bit sloppy, but hopefully it makes like a little bit of sense. And here, once again, we're just correcting the robot's path or angle as it's moving forward, because sometimes it might lean a little bit to the left on or right due to various factors. And we're just going to, so, and then once this sort of section is finished, we should be at the proper x coordinate. So now move to the proper y coordinate, given that the robot has moved to the proper x. So that's what this if statement's doing. So if y is not finished and x is finished, meaning that we've actually reached the x coordinate. So if translation.get1, so this is going to be the current y coordinate, is less than, so here we're checking this 1 inch threshold sort of rule again that we were talking about before. And then we're going to add the telemetry to say we finished the y coordinate, and then y finished equals true, and then stop the robot, because then once we finish the y coordinate, our entire process is actually done. And then otherwise, so this is a bit tricky, but move left. So moving left actually increases our y coordinate, which is a little bit strange, but it's just how it is with the axes of the playing field. So if we're less than the target x, then move left to increase our y coordinate, so that way we move closer to the target x. So that's what this line is doing. Once again, correcting the robot's natural drift or friction perhaps that occurs using the gyroscope over here. And otherwise, if it's greater, move towards the right to decrease our y coordinate, and thus moving us closer to the target y. And then once again, we're correcting for drift or friction. And then, yeah, that's pretty much, I think that's everything in the loop. Yeah. So that's pretty much that algorithm we were talking about in the previous video. And so we just implemented that pseudocode and translated it into like actual code. So it's a little bit, it has some nuances, it's not perfect. Like we had to add this 1 inch threshold sort of idea to prevent this loop from repeating itself over and over again. And also I had to correct for possible drift or friction that causes the robot to not move forward in a straight fashion, or strafe in a straight fashion. So we had to correct all of that, but it's very similar to the pseudocode. So it's just an example of how you can make pseudocode and maybe translate it into actual code. And then I'll just briefly go over these last couple of lines. So here, this is just adding data about our roll, pitch, and heading, and of those three, I said the heading was actually the most important, but since we have a gyroscope, we really don't end up using heading or any of these angles at all. We have odometry and a gyroscope, but if you didn't have odometry or gyroscope, this could be a really nice alternative. It is pretty accurate. So, and then at the end of the loop, we're just going to update the robot's location again. I think this is actually, so the first time we did that, it was outside of the loop, I think. Yeah, so the first time we did that, it was outside of the loop. As you can see, it's not within this while loop. But now, the next time we're doing it, it's within this loop. So now the robot's location is basically being constantly updated. And then, well, suppose like during this algorithm where our robot's moving in a bunch of different directions, our target is no longer visible. Then we don't want our robot to continue moving because it could cause damage, or it could just interfere with another robot, for example. So we just want to halt our robot right there and break out of the loop. So that's what this sort of line does to prevent any errors. And then finally, once everything's said and done, just stop the robot and disable the tracking once we're done. So yeah, that was a lot of information, but I hope it gives you guys a good example of like sort of how we can implement pseudocode into actual code. And okay, oh wow, this video is going on for a while, so I'll try to make the next one a little bit quicker. But we did cover a lot of the sort of initial information, so I'm going to go over this part a little bit quicker. So we looked over all of this initialization information already in the previous algorithm, so I'm just going to skip over that. Here I just created a variable for power, and this I also created a boolean for when. So this is our rotation algorithm, by the way. I forgot to mention that, but basically we're rotating the robot to the tower, or the target underneath the ultimate goal tower. So if once our robot has rotated to that, this boolean will become true. So here we have our loop while op mode is active and our duty is not done, meaning we haven't rotated. We're going to set this target visible equal to false again, and then for each Vuforia trackable in the list of trackables. Okay, so here, if the duty is done, we want to break out of this loop and just finish with the program, which is what this if statement's doing. But ignore that for now, I guess. It's not too relevant to the big scheme of the algorithm. And this line should look similar, so, or sorry, not similar, familiar. If so we're seeing if the trackable is visible out of all the trackables in the list of trackables, then we're going to update that, or update that information to the phone, and then we're going to set this variable to true because the target is actually visible. And then once again, getting the information of for the robot's location in all of these lines right here. Adding telemetry to the phone to show us where our X, Y, and Z is. And here's the calculation. So if you remember in the last video, I actually specified how you can find the calculation for the sides of the right triangle. So if you're not really sure what I'm talking about, I would highly suggest you reference the previous video, but where I had an actual nice drawing about it. But these are um, the actual calculations. So 72 minus x will be like that sort of vertical facing side of the triangle, and 36 plus translation.get1 is y. So 36 plus y will be equal to that side A of that right triangle I was talking about in the previous video. And we said we could calculate the angle theta using the arctangent of the ratio of these sides. So that's what we're going to do. So we're just decomposing the problem, and then we're going to put it all together. Here I created a variable called degrees per radian. Basically, arctan gives us a value that's in radians, but I want that to be converted to degrees because I have a method that tells me I can rotate to a certain degree angle, not a radian angle. But yeah, so I'm converting this theta value to degrees, and then here's where we actually do the calculation for theta. So math.atan, which is basically the same thing as arctangent of side B over side A, which I talked about in the previous video, times degrees per radian, so converting that to degrees. This plus 90 thing is something I did experimentally because I realized that the robot was almost always 90 degrees off when I tried to do this in person. So this is a little bit confusing because I don't really have an explanation as to why this is, but when I added 90 degrees, the robot was able to rotate to the proper angle I wanted. So this is more of an experimental thing than something that has a real explanation, so I apologize for that. But yeah, the big thing here is just this calculation that calculates the angle theta for us. So yeah, that's the main thing I wanted to highlight. Here, once again, we're updating, so we're showing the roll, pitch, and heading, and updating that to the phone, but I'm also created this other line that tells us what our calculated rotation is. Then it has the angle theta. And then, so our camera, so my idea with this program was actually to make the launcher face the tower goal, not the camera. And our camera is 180 degrees facing opposite to our launcher. So I added 180 degrees to theta in order to make the launcher face the tower. And yeah, so this basically makes the robot rotate to that angle theta. And then here, launch is just a method that launches rings. This is just mainly like, so if our robot had rings in its launcher, we could launch those rings into the tower goal, hypothetically. And then finally, since we've rotated to the tower and also launched the rings, our duty is now done, so I made this variable true, robot.stop, because our duty's done, and break out of this massive loop here. Let me just condense it. Break out of this massive loop here, and then that should also break out of this big loop actually, because duty will be done at this point, and then that'll break out of this loop as well. So there's a lot of loops going on here, but yeah. And then once it breaks out of all of those loops, we're gonna update the telemetry one more time and then stop the robot. And once again, this targets ultimate goal deactivate. So that was a lot of information. I tried to go line by line, but obviously there are some things I could be clearer about. So feel free to come to me with any questions. I understand if you don't have too much Java experience, this might be a bit overwhelming to look into at first glance, but if you understand the algorithm, I feel that's the most important part, because learning how to like translate that into code is less conceptual than actually understanding the algorithm. So yeah, understanding the algorithm is a big part, and being able to design an algorithm. So yeah, thank you so much for watching, and feel free to ask any questions.